started. Yeah, so we can either start with the remaining questions that we have from, I think, both the probit and the change point. Yeah, so anybody, if you have a update, do you want to talk about it before we move on to the new model?
I tried to implement Isaac, I was looking at your code and I tried to implement that and I ran into some problems. Like I got an error message that said that the p-value that I was getting was below 0, greater than 1, or like a NA value. And so
For change point or for I'm pulling it up now.
I guess it's the probit that.
Yeah, I think for the probit.
Mm-hmm.
Let me double check though.
Did you do, so I did a second one, which was just a copy, like a direct conversion of Professor Who's. Was it my original one?
I think it might have been, yeah, or probably your most recent. So I want to say it was the original. I can double check.
Yeah, but I'm curious about the error message that you said that you're receiving. You're saying that it's a range of p.
The second one worked for me, but it just took forever. Like I would have had to set it loose for 2 nights and then thin.
Okay.
That's
so, or I don't. It wasn't converging in a reasonable time.
but then what? Okay, so but then what is the biggest difference? I mean, because I remember when we walked through, I think a version of Isaac's code a couple of weeks ago. I think most of the stuff. I mean, when you were, I think it's mostly about G, right? We're trying to make sure that that is convergent. So the version that I wrote in R, I think we have maybe I set G to be a vector of 3, right? I set one of them to be, I mean, I forgot, is the first one, the last one is either the negative infinity or the positive infinity, and then I only have the values of G, like 2 values that I'm iterating. And so is that working now for you, Isaac, or it's some other?
So if you go into my folder, there's one that's called Hoff_V2.
Mm-hmm.
I think I put stuff for last week or 2 weeks ago.
Yeah.
And this is like, I would also be confident that like just somewhere in my original one, I had a bug and I wasn't able to find it. So maybe like rewriting it from scratch, looking at the R code helped with that. But that one I got to work. I didn't get the error Henrik was talking about. If you go down to the trace plots, it's just like, it's really slow to converge. And maybe like I set unreasonable priors or initials so that it was like just a slower convergence. But
yeah, did anybody try running the R code that I shared? I think I did, but I didn't check the results or anything. So I wonder if it's also running slow there.
Yeah, I'm sorry. I think this was the change point model, not the probit regression.
Oh, okay. All right. So yeah, so let's talk about the probit for now and then move to the change point. So yeah, but good to know that. So I think I ran it, but again, I put it together just as a way that it should be working. So so if anybody has any updates, or if you spend a little bit more time if you want to, and then figure that out. I mean, eventually, I think I'll figure it out. Yeah, Delia?
I tried running the R script, but it was taking a while for me, and I had to work on other things in R for my thesis, so I like stopped it for now. But I was looking at Nina's code from last week, and hers was like, she just kind of tried to replicate the R.
Right, I remember she said that. Okay.
It like made sense to me that way, but I'm still having problems with my computer with like the C-lang like errors, so I can't run anything with Python. But her code did seem to make sense to me in the like wording.
Yeah. All right. So I guess maybe the best way to move forward is maybe I'll just take Nina's from hers her last week's work, and then I will try to run it. And I mean, like, yeah, she was saying that she was literally trying to translate it into Python, and I don't recall what was the issue that she was running into. But anyway, I think the best way move forward from now is me take a look. Well, who knows? Maybe my R code is not running correctly anyway, or it's taking forever. I'm not sure. But at least I think that was a working version to some degree. And but I will double check. And yeah,
And no, I was saying, I think the R code worked out because again, mine was like sampling. It was just moving really, really slowly.
You mean like in R or in Python?
In Python, like because the one I did was like pretty just no longer like the mini functions I wrote, just as verbatim as possible.
Right, because you wrote those.
And it was and just looking at the trace plots, it was just clearly taking time.
Yeah. Well, like I said, I mean, yeah, like I turn our GitHub page to private because I just want to make sure that later I can summarize all of the stuff and then put a like cleaner repo later. So I do have the plan, I don't know, maybe May, at the end of May. So I will get back to you the latest by then because I do want to figure out the version in Python to make sure that it works and all that. So I just don't know if I can get back to you next week before the end of the semester, but that is on my to-do list, so I will keep you posted. So for the change point model, the issue from I guess 2 weeks ago was Elliott showed how to use PyJax to do it, and it works fine, seemed to be. We have one change point being identified, and then the lambda 1 and lambda 2, all that seems to be working and being converged and all that. And then but when Isaac ran it using a self-written heap sampler, then it turns out that the analysis has two, I think, change points, right? And then, so the results are slightly different. And I remember one of the change points that Isaac had identified is the one that is being identified using PyJax. So I guess the leftover questions for all of us from then is if you are able to run what Isaac had or change the prior in whichever way, did you find out any kind of updates or like more converging to what PyJax has done for Elliott? Anybody? It's okay if none. I mean, again, this will be another leftover, I think, that I can dig into it once I get the chance. But I think I'm guessing mostly. Well, I don't know. I'm guessing it's probably just maybe a mistake somewhere, a bug somewhere, or we just need to run it longer and all that. But I do expect to see at least. I mean, the data set is not that complicated to estimate. Not that there are a bunch of like ambiguous change points. If it's a data set like that, I guess it's possible that the self-written self-written gives does not work exactly the way as what JAX gave you. Yeah, Isaac? You muted, so.
I'm just looking at the like wrangling part I did.
And
I was wondering, I included all like tropical storms, and I don't know if other people filtered it to hurricanes, because reading the write-up or the instruction, it says hurricanes. And I don't know if like maybe there were like that could be part of it too if we're not doing it on the same.
Yeah, I remember you raised it up 2 weeks ago when we first discussed it. But I mean, a quick feedback, I think, from Elliott at that point that I think you guys wrangling the data using the same way. But that will be another thing to double check. I mean, one thing I guess, Isaac, if you have time to check is, well, once you wrangle your data in the way that you want, and then just borrow what Elliott has shared, I think it's just few lines of code, if I understood it correctly, because it's running JAX. So that might be a way to double check. I mean, if that is what it is, then that probably solved our problem. But that will be definitely another thing to keep in mind. But like I said, I will double check that, if not by next week, but definitely by the end of May, once I get the chance to clean all of the Jupyter notebooks into the ones that I want to make public. Okay. All right. So how about the new model? I mean, it's definitely, I guess, by far the most challenging one. So we can talk about it. And especially if you have questions, I mean, about the model. I gave you all of the full conditional posterior just because, well, again, we're trying to practice using Python to write a give sampler and then for a specific model. So the actual derivation, well, if you ever want to try it, it's doable. I mean, I gave you all of this, but they're all derived by people. So you should be able to do it. But I'm happy, like I said, happy to answer any questions about that. But I guess also, I guess more importantly for a group here, we want to talk about, I guess, general coding techniques there that that might help you. I mean, if you're not able to get it done this time, maybe next week is our final meeting. We're able to at least have one working version. So anybody wants to either share a screen or talk about what you have done, what kind of issues you're running into, and then everybody else feel free to jump in to share your thoughts.
Like, I guess like from the video from last class, I like was trying to follow the model, but I was wondering if like after someone presents, if we can maybe go over kind of like in a little more detail just to clarify exactly how like the model is laid out, just because I think it's just a lot of elements together.
Sure. So maybe, okay, let me put it up. I think
And I don't know if
okay.
anyone feels the same way, but yeah, I thought it was kind of complicated.
Yeah, I was having a hard time following also.
Okay. So let me put out the documents. I think, right, okay, it's here. So let me share my screen. Just give me a second. And happy to describe the model a little bit more and then answer any questions you have. So the coding, if I have to guess, well, I mean, even though I gave you all of the full conditionals, it probably still be challenging overall. So definitely we can talk about it once we go through the model. So yeah, so this is a model that when you have multiple categorical variables you're trying to model at the same time. Okay, so you still have in this case n observations. Okay, and each observation has p categorical variables. Okay, so what this is trying to do is to model all of the categorical variables at the same time. Right, so we have done this, say for example, the probit regression that we did, even though we didn't completely solve it, but there each observation is having a univariate ordered categorical outcome, and then we're using a probit regression to do that. Here we have multiple variables and we're using p to represent how many there are. Okay, so when we write this xi, we're talking about a vector for each observation. Okay, so it's xi1 to xip. Okay, and specifically we are using a latent class model here that we assume that each observation belongs to one of the k, capital K, number of underlying latent class. And we have seen this latent class modeling, I think towards the end of the Bayesian course, that we looked at a case study where we have a group of students or a group of test takers seems to be random guessing, right, the scores, and then the other group seems to be the knowledgeable group. So there, you can either do a hierarchical model like most of you did, I think, in the first round, when you try to, well, assume that some people belong to one group, the other people belong to the other group, and then I try to make inference about the group success rate, for example, because it's a random, it is a, I think, multiple choice question, so you can think about P as the success rate of answering each question right. So you have naturally two groups there, and the reason why instead of using a hierarchical model, but then use a what we call latent class model, is because there, especially for those scores that are sort of in between the two groups, it's hard to like classify this into either group, right? So it's possible that we don't know exactly which group that observation belongs to, and we want to be flexible about it. So that's what we mean by latent class. In that example, you only have two classes, because either is the knowledgeable group or the random guessing group. Here we're doing much more, I mean, more general. We have capital K here, number of groups or latent classes, and we assume that each observation belongs to one of those. Okay, so that's what this equation 2 is about. We have this Zi as the indicator of the latent class assignment for observation I. And you can see that it comes from a multinomial distribution, right? Pi 1 to pi k. So we know that pi 1 through pi k, they add up to 1. So that means the Zi is any of the case. Okay, it would take one value, and then it will be any of the case here. Okay. Then once you have determined what zi is, we're saying that the jth observation, the jth variable of the ith observation xij will follow a multinomial distribution because it's a unordered categorical variable. So many things are put together in this way, but the one I would recommend to think about the model equation 1 and 2 in the backward order, that you think about 2 first. That's how you assign how each person goes into what class or latent class. And then once you have assigned which class each person goes to, then each variable independently follows its own multinomial distribution. Okay. So that's what it is. And then I gave you a bunch of complicated prior distributions for this model. So happy to talk through more about this later, I guess. But like I said, section 2 of this document gave you all of the full conditional posterior distribution. Okay, so you know that this is implementable by a Gibbs sampler because all of the full conditional posterior is ready. So for this one, for example, step 1, we have seen this in the change point model, right? We can get the probability, normalized probability for zi to be any of the k. And then we do that for all of the k's, and then we take another multinomial. Okay? So we have seen this technique before, it's just in a different context here. Okay? And then you have some other parameters, but I gave you all of the full conditional posterior distribution. So definitely, if you look at how, I guess, complicated those full conditional posterior distribution look, you probably know that you have to do a lot of bookkeeping to make sure that you're getting the dimension right and all that. So I think that might be, we can talk about it now if any one of you feels comfortable to share what you have done, and then we can answer questions from there, if that makes sense. Okay, I can stop share here, and we can see who wants to share. If you have anything, if not, we can talk about what you can do to code the skip sampler given what's given to you. Yeah, Isaac.
I would say so I cut one up. My question is, how do you do post? So like trace plots should make sense. How do you do posterior predictive? Here, do you like sample z from pi every time?
Yeah. So what you do is, okay, so let me come back here. Yeah, so Isaac's question.
And if you're drawing like randomly from pi, couldn't you be losing a like certain entries natural cluster?
Yeah, good point. Okay, so first of all, the first part of Isaac's question is if we have, okay, so all of this are the parameters, right? Like you have zi, pi k, and then theta k, j, and alpha. So how can you do, so once you run, so suppose we are able to run an MCMC, and then you get a bunch of posterior draws of these parameters. The way to do posterior predictive checks in this case is, well, remember, posterior predictive checks is we have to generate data, right? Generate data based on the estimation that you have done. So if you go back to, so equation 1 and 2, these are how data are generated, right? So you should go to equation 2. So first of all, for each zi, you take a multinomial draw at that iteration of your pi's. So you get zi for each one. And then, of course, then for each xij, you have to go into each of the different variables, j from 1 to p, and then do the multinomial draws based on the parameters you have over there. Right? So this is actually what we mean by a generative model. The model is, I mean, the way that we wrote the model is showing it as how the data can be generated. So posterior predictive checks can be done there. To answer the second part of what Isaac was asking, so this is, well, I would say it's possible some of the clusters are very little populated at a particular iteration. Say if your k, I don't know, if you set your k to be 10, for example, and then maybe only the first 9 are really being utilized, and the last one, k, capital K, like the last one, the 10th cluster, like at a particular iteration, you just don't have any like any observations being clustered there. So naturally, I think when you simulate ZIs for posterior predictive checks, then that will mean that your pi 10 will be maybe close to 0. So whenever you're making a multinomial draw, it's very unlikely, I guess, to get a cluster, get an observation to be coming from the last cluster. So it's possible, but I think overall, well, it is, I shouldn't say it is what it is, but the model is written and come up in this way. And overall, I think this kind of model is really trying to be flexible, that even though we allow up to capital K number of latent classes, but we're really letting the data to decide how many clusters are really being used. Okay? And the thing is, we cluster observations based on, as you can see, all of their attributes, all of their variables, each of the xij. Right? So we're hoping to cluster observations based on all the information that they have. And then each cluster should just have observations with similar characteristics based on the P categorical variables. So if you turn out to say your capital K is 10 and then only the first 9 are really used and the last one is not used, then imagine that, first of all, it's very unlikely for the posterior predictive checks for you to get any observation from that one anyway, but also because the clustering algorithm, in some sense, in this case, do not cluster any observations there, then any kind of estimation that you're able to do for that cluster will be very, very not good either, because you don't have many observations there. Okay? So this, if you look at, especially here, step 3 here, okay, if you look at what we're doing here, in order to, so you can think of this as, so theta kj is estimating the multinomial probability for the jth variable for the kth cluster, right? And you can see that, well, it has the prior, it's a Dirichlet, so it's actually a Dirichlet multinomial conjugate. And you can see that you actually have to count how many observations are there, right? Going into the cluster and then sharing the same level. So it really depends on how many observations are being clustered there for you to update your probability vector. So in some sense, if one cluster is very little populated, then you won't have many observations to be used to estimate your probability vectors. In some sense, I mean, that estimation wouldn't be really good anyway. But I mean, on the other way, you will see that, well, when you're doing posterior predictive checks, you wouldn't be generating a lot of observations from that either. Maybe I went too far. Maybe that is, well, maybe without that much, you already got it, or I confused you a little bit even more.
That makes sense to me.
Okay, good.
Yeah, that was helpful.
Yeah, I also thought that was helpful.
Okay, thank you. So how about, yeah, I mean, if anyone has anything to share, we can talk through them. And I mean, if not, my backup plan is I do have a version of this in R and I can share it with you. But of course, I mean, before doing that, it will be good to talk through, I guess, some of the challenges that you're facing when you, I mean, maybe trying to understand it. Yeah, Isaac?
I have one just on like efficiency. I
Sure.
don't know. So for the, I'm gonna pull up a copy real quick too.
Sure. Yeah.
So I have the model in front of me, and I'll share screen in a sec.
Yeah, and actually, as I go through the work, I mean, the one that I share with you, I think there's a typo somewhere in step 3, but I'll update it. And I think I accidentally have some F there. Those F should be K. So it's step 3 when I wrote it. So, but the expression itself is correct. I think it's just the wording. I had some extra term there. But yeah, Isaac, feel free to share your screen.
Yeah, here, I'll share screen.
Okay.
So it should be the write-up.
Yeah.
So my question is for just like making the issue with micros just takes forever to run, and it's because of one step. So I wrote a like helper that does this chunk here, on its own on the log scale.
Mm-hmm.
Because you have to like go in and get the right probability.
Mm-hmm.
And then one that iterates over that. So in my code, I have like a function for drawing a single ZI, which like I'm fine with, but and I like flip everything to having been one hot encoded so that like you can just multiply and then take sums to extract probabilities. But like it's this line right here takes like 2 seconds per iteration to run. And I didn't know if anyone like had a more like a less expensive way of calculating the Z's, all 10,000 of them. Because I can like, if I do like 200 iterations, I can go like make myself lunch, come back, and it'll be just finishing up.
Right.
Which
right.
is not what I want.
Yeah, I see. So I guess you are sort of writing it. Can we go to your code? Yeah.
Yeah.
So you have your pi_k, and let's see. Right, you have your pi_k.
So I'm doing like each component for k.
Yeah.
And then.
Yeah. I wonder. Let's see. Because the pi_k will be, well, from whatever the iteration before, right? You will have the bunch of k, or if that's the first one that you're simulating, then you initialize it. So that pi_k, I think, is a fixed vector. So I guess.
And that comes in here.
Right. Yeah, it comes in there. So I wonder. Well, I don't know if that will be a way, but I wonder, since if you. So you're writing a loop going through each of the k.
Yeah, and my, like, as you can see, I think when you take a draw of a full Z, you have to go all over all 10,000 Z.
Yeah.
Then you have to go over all of the P.
Right.
And you have to go over all of the K. And I just don't know how to write it with a, and then all over the K. I don't know how to write that, like, loop in fewer steps.
Right. Because right now you have one loop going through the k, I guess.
Yeah.
Yeah, for each of the ZI.
And then so you do that, and that gets you for each K,
Yeah.
like this thing.
Right, I think so, yeah.
And then at the end, I sum them all up.
Yeah, that would be what I would do
But
in the first place. Yeah, go ahead. Sorry, I missed it.
It amounts to like 3 nested loops, which is like why it takes, I imagine.
Yeah.
Like there's just no escaping it taking that long.
Yeah, Z, I'm sure among all of the parameters will be the one taking the longest time to run, just because how it is done. I wonder if there's one, let's see. Does it make sense to, because in R, I wonder if like, say, since pi is the same, or like all of the pi k's are the same and the theta are given, so is there any way to, say, for the for loop of the k that you wrote for your draw Ci, I wonder if there's a way to do it as a matrix multiplication instead of doing the loop. But that might be too naive. I don't know. Like, depends on the model itself.
Because then you just like, because you have to keep the parallels. I'm thinking just across like different dimensions of P too.
Right, that's true. So, oh, I see. Because then you have a for loop here for the P, and okay, I see. Yeah, I don't know an answer on the top of my head, but anybody else has any?
I just didn't know if anyone had like a faster way of getting through this part of the sample.
But the other parts are okay for you working? I mean, the other ones are running, only this part is taking long?
Yeah, it's the chunk highlighted here that's like,
I see.
take a couple of seconds each iteration.
Yeah. Each iteration for 10,000 observations, right?
Yeah.
Okay.
And then.
Yeah, I see. So then if you want to run it for a larger number of times, then, okay.
Or like a couple of seconds to get through the 10,000 rows, but then like for burning in and thinning.
Yeah, Yeah. I mean, I guess typically we set it run for 5,000 burn in, right? And then run another 5,000, say, and then that will be 10,000 in total. So yeah, it will be some time, of course. And yeah, I will think about it. And then, like I said, I think I will share the version that I have in R. I have to, well, I probably won't be able to make sure that it's definitely running, but it will be some, like maybe a good starting point for you to get started. And like I said, I think I have a couple of, yeah, at least I saw one typo in the document about step 3 in the description. So that will be something I will update after we end the call, and then I will update it to our GitHub page as well. Yeah. But this type of model, just like what Isaac pointed out, this type of the model, especially late in class, sampling the late in class assignment will always be the hardest one. I mean, I wouldn't say hardest, but will always be the one that's taking the longest. If you think about it, I mean, because we have to go through each of the observation, right? So the index, I mean, the loop that you're going through is for each I. And for each I, it looks like, based on the one that we have seen right now, the setup is just, yeah, you have to go through the pi, you have to go through the theta, and it's definitely overall complicated to do. So it might be the best that what Isaac has come up with already. Like I will maybe the fastest, but again, I actually don't know much about Python. But like say for example, this kind of stuff, if you try to code it in try to code it in R, a lot of times this kind of nested loop, people will write that part in C, and then trying to utilize. Yeah, go ahead.
I know over some certain number of iterations, because it's like more directly points at C. Like there's some threshold where the R's apply functions get faster than Python.
Yeah. So
I don't know what the cutoff is, or if we're above or below that here, but
I'm not too sure. So that might be another thing that maybe we won't be able to solve it like within an independent study like this, but maybe in the future, if you ever see that some way, I don't know, like I'm not an expert there at all about how to optimize the code, and then let alone in Python. I mean, for me in R, just, okay, let's move that part to C and then use that. So it's definitely challenging, but most like, I mean, for this part, at least, I think what Isaac has done, and I hope once I post the R code and then everybody else in the call will be able to try that as well. Based on the full conditional posteriors, how much you can write the give sampler in Python. And then the next step, of course, is to think about how to speed it up. And then on top of my head, I don't know if there is any better way, but I will keep looking, and then you can all keep looking. Okay. Yeah, sounds good. So what I would do is I will put the R code that I have, and then I will post it, and I'll update this document just to clean the typos, and then hopefully next time, which will be our last meeting actually, we all have something working, and then to make sure that we can, well, implement the model. And I think I share with you all the data, so you have something to run it with, and then to see if that works for you. Okay. All right. Sounds good. Okay. All right. So any more questions, comments? Next week will be the last day, because that's the last day of bachelor's, last day, I think. Yeah, a Wednesday. And most likely we'll end there. And yeah, like I said, if I see any other updates, especially based on the previous models that we didn't get clear, later on I might email you if I figured out what to do. And you all still have access, I think, to the GitHub page. So yeah, I just made it private, but should be accessible to all of you because you're all contributors, I think. Okay. All right. Okay, sounds good. And I will see you next week for the last time.
Thank you.
Y'all take care.
thank you.
Mm-hmm.